Yeah, today we'll start with uh, next PISO. Okay, parallel in serial out. Okay, hope my screen is visible. Okay, yeah, one second. Yeah, so next today we'll discuss about one more topic, that is PISO, parallel in serial out. Okay, this is nothing but parallel in and serial out. Okay, so if you see the PISO, you have so you have so this is my PISO. So what are the inputs you have? You have clock and next reset and one more that is load is there. One more input, that is load is there, and you are loading the data parallel underscore in. Okay, parallel underscore in, and next serial underscore out. Okay, so here so anyway this clock is 1 bit. Okay, this is reset is also 1 bit, and load also 1 bit, and parallel in data. So parallel in data means you are loading 4 bits of data. This is 4 bits, and serial out, so serial out is only, also 1 bit only. Okay, serial you are taking out the data. Okay, so here so logic is like within one clock cycle we are loading the data. Okay, so first one clock cycle we are loading the data. Okay, we are loading 4 bits of data. Okay, loading the data, and next after means next 4 clock cycles you are doing shifting the data. Okay, shifting the data. Okay, so first you are loading the data and next you are shifting the data. So that means there is a control signal, that is load. Okay, when load equal to 1, what you are doing, whatever the data, so data will be there in the temp register, you are initializing to data. Okay, so data you are loading in the temp register, you are initializing the in this data. Okay, data, and when load equal to 0, what you are doing, you are doing the shift operation, shifting. So whatever the shifting is there we are doing. Okay, so this is the operation. So first so that means there is a there is a pin called load by shift bar. Okay, load by shift bar, that is equal to 1 means it will do load operation, and load by shift bar, that is equal to 0 means this will do shift operation. Okay, shift operation. Okay, so how you are doing the shift operation? So first so here you are loading the data. Suppose let us take the index 3210. Okay, this is the index. Okay, first you are loading, so that means here when load equal to 1. Okay, load equal to 1, you are loading the data, no? So let us take 1111, you are loading the data. Okay, after that after next clock pulse, this is first clock pulse. Okay, at second clock pulse what you are doing, that means you are shifting the data. Okay, this will go. Okay, this will go and this will come here. Okay, one will come here and this one will come here and this one will come here. Okay, you are doing left shift operation, whatever the vacant position is there, that will be loaded with 0. Okay, and at third clock pulse this will go, and this one you are shifting, and this one you are shifting, one you are shifting, and 0 will come here, and whatever the vacant position is there, that will be loaded with 0. Okay, at fourth clock pulse what you are doing, this will the 1 will go and 1 will be shifted here, and 0 will be shifted here, and 0 will be shifted here, and whatever the vacant position is there, that will be loaded with 0. Okay, at fifth clock pulse total whatever the data is there, that data is available at the that is this one. Okay, so this will be available. Okay, 1 bit will be available, and so this will be shifted, 0 will be shifted, and this 0 will be shifted, and this 0 will be shifted, and whatever the vacant position is there, this will be loaded with a 0. Okay, so here what happens, that means you need to develop a logic. Okay, so like every time so what is the logic, same as SISO only. So every time this 2 down to 0, this 1 to 3, it is copying, no? Second clock pulse it is copying. Okay, and at the third clock pulse 110. Okay, 110 is copying over here. Okay, at 4th clock pulse, this 11100 it is copying over here. Okay, and every time from the left you are loading the data. So how you can write that is temp. Okay, temp you are initializing to what? So temp non-blocking with so that is temp 2 down to 0 comma 0. Okay, temp 2 down to 0 comma 0, and where you are getting the data, so that is serial out data. So that means serial out data you need to initialize to what? Serial out, serial underscore out. So you are initializing to where you are getting at temp 3, no, at temp 3 you are getting the data. So that is temp this is 3. Did you understood the logic, PISO? Shall I move forward?
Yes.
Okay, what about others? Okay, so I will begin with the code. Okay, yeah, I will begin with the code. So here module PISO, my module name is PISO. Okay, input. Okay, input, what are the input? Clock, reset, and so parallel data is there, no? One second. So parallel, whatever the parallel data is there, so that parallel data here you are loading with that is 3-bit data, no? So 3-bit data, so that is input that is 3 down to 0 parallel underscore in. Okay, and next input whatever that control pin is there, that is load. Okay, when load equal to 1 it will do load operation, and load equal to 0 it will do shift operation. Okay, that is nothing but load, and output serial underscore out. Okay, this is 1 bit of data. Okay, so I am declaring the inputs and outputs. Okay, and next what I need to do, I need to declare one temp register, that is reg 3 down to 0. This is 4-bit temp register, so that is temp. Okay, after that always at the rate passage of clock, so what you are doing, if reset, that means if reset equal to 1, I am initializing the temp with what? Temp with 4 tick binary, all zeros. Okay, 4 zeros. Okay, else if, okay, else if it is load. Okay, if load equal to 1, I need to load the temp register with what? That is 4 bits of data, that is 4 tick binary 1111. Okay, I need to load with so that is or if load equal to 1, I need to load with parallel data, no, sorry, I need to load with parallel data. So what is the parallel data? I need to load with parallel underscore in. Okay, so that is a 4-bit data. Temp is initialized with the parallel underscore in. Okay, parallel underscore in, and else. Okay, else if when load. Okay, so when load equal to 0, I am using a relational operator. When load equal to 0, so what I am doing, temp is non-blocking with so I am using concatenation operator, temp. So what is this? Temp 2 down to 0 comma 0. Okay, from left hand side, so initially I told you the logic, no? So that means temp equal to temp 2 down to 0 comma 0, every time that will be copied. Okay, end, and after that I am using assign statement. Okay, assign. Okay, so assign, so if it is assign, I need to use this one as blocking assignment. Okay, so assign, yeah, so so I need to use assign statement. Assign, what is the serial out data? Serial out. Okay, serial out equal to what? Where you are getting serial out data? Serial out that is equal to what? Temp 3. Serial out data equal to temp 3 and end module. Did you understood this code? So this is the Verilog code for PISO, parallel in serial out. Is there any doubts or queries in this?
No.
Okay. Okay, this is a PISO, and next we'll see with the PIPO. Okay, last case, this is PIPO. Okay, Verilog code for a PIPO, parallel in, parallel out. Okay, parallel in, parallel out. Okay, so PIPO, if you take, so if you see the Verilog code or RTL code, okay, RTL code. So you have PIPO. This is my PIPO. Okay, so you have input clock. Okay, this is my PIPO, parallel in, parallel out. You have reset, and next you have parallel in data, that is, this is also input. Okay, and one more load is there, and next you have the output parallel out, parallel underscore out. Okay, so here this one is so this one clock is 1 bit and reset is 1 bit, and parallel in how many bit? 4 bit, and load bit is 1 bit, and output parallel out is 4 bit. Okay, so how to write the code for this? So let us take, so I'll start with module, and what is my module name? Let us take PIPO. Okay, PIPO, and I need to declare input clock and reset, input clock reset, and input load and input so what is parallel in data? I'm using a vector 4-bit data, so 3 down to 0, parallel underscore in, and output, okay, output I'm initializing with reg data type, reg 3 down to 0, parallel underscore out. Okay, so why you are using means, so this parallel out I am using in the behavioral modeling, that's why I'm using port rule connections, you need to see. So that means output should be reg data type. Okay, so always at the rate passage of clock, okay, if reset, that means if reset equal to 1, parallel out, so parallel underscore out. Okay, first you need to apply the reset. Okay, so non-blocking with what? 4-tick binary 0 0 0 0. Okay, non-blocking with 4-tick binary 0 0 0 0, else if load. So when load equal to 1, what you need to do within the 1 clock cycle? So in PIPO we already discussed in the digital, within a 1 clock cycle, parallel that is parallel load, that means parallel in load operation, and taking out the data. Parallelly you will load the data, and parallelly you can take the data within 1 clock cycle. Okay, so that means when if load, so parallel out, so whatever the parallel in data is there, that is coming to the parallel out. Simple. That is coming to the parallel out. Okay, and end, and so always at the passage of clock, here you need to write begin and end module. So did you understood this code?
Yes.
Okay, so I will show you in the Vivado how to execute these codes for all this SISO, SIPO, PISO, PIPO. First we seen about the first we will see the SISO left shift. Okay, this code we already discussed, okay, in the last class. So that means here you need to declare one second, this is SIPO, this is SIPO, SISO, this is SISO. Okay, so module SISO left shift input clock reset D in and D out. Okay, and I'm declaring a temporary register reg 3 down to 0 temp, always at the rate passage of clock or negate of reset. This is asynchronous active low reset I am using. Okay, asynchronous active low reset begin, So asynchronous active low reset means what? If reset equal to 0, I am clearing all the bits. Temp equal to what? 4 tick binary 0 0 0. Else, so I told you the shift operation. No, left shift means what? Temp is non-blocking with temp 2 down to 0 comma whatever the serial in data is there. Here you can consider D in also, D in. So by using concatenation operation, I am giving this data end, and at last where you are getting the serial in serial out data, that is D out equal to what? At temp 3 the serial out data is available. Okay, serial out data and end module. Okay, and coming to the test bench also. So if you see the test bench, this is the test bench. So module TB SISO left shift. So whatever the means clock reset and DIN are there, those are initialized with reg variable, reg data type, and DOT you are declaring with Y data type. So that means declaring the internal variables. And step 2 is nothing but you need to instantiate the design in the test bench. So how to instantiate? That is design name. My design name is SISO underscore left shift DUT, and I am using connection by position. And step 3 is clock generation. Always #5 clock equal to not off clock. And step 4 is you need to initialize the reg variables, initial begin, and clock equal to 0, reset equal to 0, and DIN equal to 0. After that you are here you are asserting the reset. After 10 time minutes you are deasserting the reset, and you are giving some value. DIN equal to like 1 after 10 time minutes, DIN equal to 0, and DIN equal to 1 for after 10 time minutes, and DIN equal to 0. Okay, so you can change the values also. So whatever in our example 111, no? So here we will check for 101. Okay, after that wait for observe the output for 30 time minutes, and $finish is nothing but system task. We need to end the simulation. We are using $finish end and end module. Okay, so this one I want to execute. Okay, how to execute? So how to execute this? So whatever the simulation you are doing, you need to set a stop module. Okay, right click, set a stop, SISO left shift. Okay, suppose if you want to elaborate the design, and just save. You can see the like we will actually we will design the shift registers by using D flip flops. Okay, so 4-bit shift registers means you need 4 D flip flops are required. Okay, that I think you hope you have the idea about digital. In the digital we see in the shift registers. Okay, so mostly counters we already discussed that counters we will design by using T flip flop and JK flip flop, that too operated in which mode means toggle mode. Okay, see here, so 4 D flip flops are there. Okay, so 4 D flip flops initially. So this is how the so reset, clock, D in and D out. Okay, and coming to the simulation, run behavioral simulation. So if you see the simulation in the test bench, I am not given any $display or $monitor statement. So in TCL console it will not execute. Just you need to see in the waveform only. So see here. So when the reset equal to 0, D out equal to 0 only. Okay. So when reset equal to 1 for 10 time minutes, you are applying the reset. Okay. After 10 time minutes, what you are doing? That means reset you are deassetting. You are making reset equal to 1. So when you are making reset equal to 1, so during this passage of clock, first it is getting at what? So first serial load is happening. Okay, so this is nothing but 1, and during this next passage of clock, next 0, and next passage of clock 1, and next passage of clock 0. Okay, so next what happens? So this is loaded in the temp register. Okay, so that means loading of data is happening. Okay, serial load is happening. After that, after loading of data, so that will be available at the after the shifting operation is happening. Shifting operation that will be available at temp3 register. Temp3 register you are initializing to D out, no? So during next clock pulse, 1 is coming, and during this clock pulse 0 is coming, and during this passage of clock 1 is coming, and during this passage of clock 0 is coming. Okay, till that means till 40 10, 20, 30, 40 shifting operation. From 40 loading operation, first 10 to 40 loading operation means serial shift is happening, and 40 to 70 shifting operation is happening. So have you understood this SISO left shift? Any doubts or queries?
No.
Okay, this is nothing but SISO. And next what we have seen PISO, no? So this is nothing but PISO. Okay, so code I already explained, like parallel in, serial out. So here if you want to see the code, parallel in, serial out. So today we see SIPO, no? Yeah. So module PISO, so input clock, input reset, input load, and parallel data. So data input you need to declare with parallel 3 down to 0 parallel in, and serial out, that is D out, that is 1 bit. You need to declare one temporary register, reg 3 down to 0, shift underscore register. Always at the rate passage of clock or negate of reset begin. If not of reset, if reset equal to 0, I am initializing the shift underscore register with all zeros. Else if load means what? Parallel load. Okay, shift underscore register equal to, I'm using concatenation operator, d in of 3, 2 or 1 and 0. Okay, you can use d in also, it will take. Okay, and else, so serial out means what? Shift underscore register, that is every time 2 down to 0 will be copied, and whatever the vacant position is there, that will be loaded with 0. Okay, so inside the LSB with 0, and need to assign DOT equal to what? At where you are getting serial out data. So serial out data is getting at the reg 3, shift underscore reg 3 or temp 3. Okay, so this is the code. And coming to the test bench, so this I need to set as top module. Next this is PISO, no? PISO UC, yeah, this also you need to set as top module, cd underscore PISO. Okay, parallel in, serial out. Okay, so that means here so module TB PISO, so clock, reset, load, and d and 3 down to 0 d in need to declare with reg data type, and d out we need to declare with y data type. And I'm instantiating the design. So this is connection by name. Whatever the variables outside the bracket are nothing but design inputs and outputs. Whatever the variables inside the bracket are nothing but test bench variables. And next we need to generate the clock, always #y clock equal to not of clock. And I need to initialize the reg variables. Okay, clock, reset, load, and d in also you need to initialize with these are the reg variables. No, you need to initialize with 0, and apply reset for 10 time units, and after 10 time units we are making load equal to 1, and parallel load means I am loading 1010. After that I am making load equal to 0. So after that it will do shift operation, no? So observe the serial out for 80 time units, $finish end and end module. Okay, this is the test bench. Okay, so go to the simulation, run behavioral simulation. So just go to this simulation, fit to page. First what happening? First during this parallel load is happening. Okay, when load equal to 1, so parallel data, so that is 1010 is loading. Okay, so that means see here A. Okay, A means what here? Parallel load. So parallel load means A. So otherwise just right click, radix, binary. Okay, binary means what? First when load equal to so when load equal to 1, parallel load is happening 1010. Okay, after that when load equal to 0, so shift operation is happening. Okay, here you are getting the, so first loading, so here loading operation is happening, and after that 1010, this is shift operation 1. So during this passage of clock, 1 is coming in the D out register, and during this passage of clock 0 is coming. Okay, and during this passage of clock 1 is coming, and during this passage of clock 0 is coming. Shifting operation is happening. Okay, so this is how you need to see the simulation for PISO. Is this fine? Any doubts or queries in this?
Fine.
Okay. Yeah. So this is what we seen PISO, and today we seen the what we call SIPO. Okay, SIPO. So just set as top module, and SIPO TB set as top module, and so SIPO. This is SIPO. So SIPO means you need to declare the inputs. Okay, input clock reset D in and output. So output is parallel out, no. So that is 3 down to 0 D out. I need to declare the temporary register, that is shift underscore register. Always at the rate passage of clock or negate of reset begin. If not of reset, if reset equal to 0, shift underscore register equal to, you are clearing the all the registers. Else, so what you are doing? So that means I told you the logic. That is so from left you are entering, you are shifting, means you are loading the data serially. Okay, so shift underscore register is non-blocking with every time 2 down to 0 is copying, no. So that is shift underscore register 2 down to 0 comma D in. Okay, D in. So this is left shift insertion end. Okay, so behavioral modeling is ended. After that, what you need to do, you need to use a continuous assignment statement assign. So where you are getting, that is you are getting a temp 3, no, that is parallel out. Okay, so your parallel serial in inserting the data serially, and 4 bits of data you are taking out. Okay, so the data is available at the temp register, no. So I told you in the that your data is available at the shift underscore register. This is 4-bit data that is assigned to D out and end module. And coming to the test bench SIPO, so we need to declare clock reset and D in with reg variables, reg data type, and D out with the Y data type 3 down to 0, and you need to initialize connection by name. Okay, and after that you need to generate the clock hash5. Process is same only. Okay, and hash5 clock equal to not of clock, and initializing the reg variables. After 10 time minutes you are deassetting the reset, and you are sending the values. Okay, so let us take 1010. Okay, 1010, and so first serial data you are sending. After that serial data you need to get. Okay, after 20 time minutes you are observing, and you are finishing the simulation. Okay, so just we'll see this. So I set as top module, run simulation. Okay, I am saving this code. Okay, 1 second. So fit to page, SIPO. So every time what happening, so when so 1 second, which one it is loading? TB SIPO. Okay, yeah, set as top module, run simulation, run behavioral simulation. Yeah, serial in data. Every time serial in data is loading. No, serial in data means yeah. So this one first what happening? When reset equal to 0, all outputs will be 0 only. When reset equal to 1, during this passage of clock, so first data. So first data means this is 0 will be loaded. Okay, again second. So like 0 1 0. Okay, second will be loaded, and 5 1 0 1, and B. So like this it will be loaded, and after that you are getting, so like this. So 1 2 5 B. These are the values. Okay, right click, and I want to see in the binary. Okay, every time that is shift operation is happening, no. So like 0 0 1 0 1 0 0 1 0 1 and 1 0 1 0. Okay, like that 1 0 1 0 you are getting. Okay, So 1010 you are getting, that means shift operation is happening. Okay, that means loading the data serially. Okay, not shift operation, loading the data serially. Every time from the left shift you are loading the data. Okay, so first clock pulse, this is 0001, second clock pulse 0010, third clock pulse 0101, fourth clock pulse all data is coming. Okay, and again after that at fifth clock pulse you are getting 1111. Okay, so like this is nothing but is a PISO. Okay, in the test bench if I give 1111, we'll check what we are getting. Save this. Okay, run the simulation, run the behavioral simulation. So see in the fit to page, see here, now it is clear. So right click, radix, I want to see in binary. Okay, first shift means loading the data serially. Okay, first 0001, 0011, 011. So after this 111 is loading, and at a time next clock pulse what happens, it is taking out. Okay, taking out the data. So 1111 it is coming at D out. Okay, so like this we can see. Okay, so this is, so every time 11 is coming in the D in. Okay, so this is serial in parallel out. Okay, next parallel in parallel out. If you see the parallel in parallel out, this is parallel in parallel out, test bench and code. So parallel in parallel out means whatever I explained. So you need to declare module PIPO. So input clock, input reset. So data in you are declaring with 4 bits of data with vector 3 down to 0, and output also you are declaring for D out, that is 4 bit of data 3 down to 0. Reg 3 down to 0, reg 3 down to 0, reg underscore data. This is like a temp register only. Okay, always at the rate passage of clock or negate of reset begin. If not of reset, okay, if reset equal to 0, what you are doing, reg underscore data you are clearing to 0. Okay, otherwise else you are loading the data. Okay, you are loading the data at last end, and I am assigning D out equal to what, reg underscore data. Okay, parallelly within one clock cycle, parallelly loading the data, and parallelly you are taking out the data. Okay, so here what you need to do, so run simulation, run behavioral simulation. So open this, one second, fit to page. So we'll see the test bench. Okay, test bench TB. So you need to declare the clock reset and D in as reg data type, and D out as wide data type, and you need to instantiate connection by name, always #5 clock equal to not of clock, and you need to declare the reg variables with 0, and you are deassetting the reset. So here what parallel output, parallel data you are giving 1010. Okay, and next 1100, and 1010 means nothing but A, no, 1100 means C. Okay, 011 means you are giving 7. Okay, so for 20 time minutes, after 20 time minutes you are closing the simulation. Okay, you are ending the simulation. Okay, so this is the test bench, based on test bench only you will get. Okay, so run simulation, run behavioral simulation. So see this, first what we given. So during this reset equal to 0, you are getting data out equal to 0 only. Okay, again during this passage of clock, first you are loading which data, 1010, no, so radix binary. Okay, so 1010 is coming at the data out, radix binary. Okay, 1010 is coming. Okay, during this passage of clock. Okay, again during this passage of clock, 1100 is coming at the data out. Okay, again during this passage of clock, 011 is coming. Okay, so this is nothing but parallel in parallel out. Okay, So we see in all the cases, that is serial in, serial out, left shift, and serial in, parallel out, parallel in, serial out, parallel in, parallel out. Is this fine? Any doubts or queries in this? Is the coding is fine?
Yes, fine.
What about others? Okay. Okay. So yeah. Next, we'll start with one more topic, one more new topic. That is nothing but one second. Where is my pen? Yeah, we'll start with one more new topic, that is nothing but RAM design. Okay. So FSMs we'll see in the tomorrow next class. Okay. Today we'll see the RAM design. Okay. So what is this RAM design and how to design this RAM? So we'll discuss. Okay. So RAM. What is RAM? RAM is nothing but random access memory. Okay, random access memory. Random access memory. Okay, so RAM. So if you see the RAM, basically I am designing 8x8 RAM. 8x8 RAM. Okay, so 8x8 RAM, if you see, so you have RAM. This is my RAM. Okay, so this is my RAM. So you have clock, reset, and next you have write enable, and next you have read enable. Okay, and next you have data in, data underscore in. Okay, and you have write address. Okay, so input, this is input only, here I am writing write address, and next you have read address. Okay, read address, and next output is data underscore out. Okay, so here if you observe this, that means this is how many bit? This is 1 bit only. This is 1 bit. Reset is 1 bit. Write enable and read enable, this is also 1 bit only. Write enable and read enable, this is 1 bit. Data underscore in is 8 bit. Okay, 8 bit. And write address. Okay, so write address means what? This is 8x8 RAM means. So that is so address will be what? 3 bit. Read address and write address is all are 3 bit. Okay, so read address and write address is 3 bit, and data out is 8 bit. Okay, so here what you are doing, like so if you see the RAM, 8x8 RAM, so if you see the 8x8 RAM, so total how many locations you have? Can anyone say how many locations you have? 0, 1, 2 up to 7. So total 8 locations you have. Okay, this is nothing but number of locations. So number of locations are nothing but 8. Number of locations 8. Okay, and what this is nothing but we call as depth of the location. And here each location we can accommodate how many bits of data? 8 bits of data, 0, 1, 2 up to 7. Okay, so this is we call as so width. What is the width of the width equal to 8. Okay, so width equal to 8. So this is nothing but my RAM. Okay, so total depth of the RAM is 8. Depth of the RAM is 8 and width of the RAM is 8. Okay, so that's why RAM is initialized in terms of 1 bytes. So byte, 1 byte equal to how many bits? 1 byte equal to 1 byte equal to 8 bits. Okay, you know this. 1 nibble equal to how many bits? 4 bits. Okay, 4 bits. And half word equal to what? Half word equal to 16 bits, and one word equal to 32 bits. Okay, you have that RAM is initialized like 1 kilobyte. 1 kilobyte is 2 power 10 locations are there. 1 megabyte, so megabyte is 2 power 20 locations. 1 gigabyte, you have 2 power 30 locations. 1 terabyte is 2 power 40 locations. Like this, this is the size of the RAM. Okay, so we are designing the RAM, no? So you have so here there are steps are there. What is the first step? First, you need to make write enable. Okay, write underscore enable, that is equal to 1. Okay, so we should make this signal to 1 in order to write any data into RAM. Okay, so we should make this signal to 1. Okay, in order to write any data. Okay, if you want to write any data, you need to make write enable equal to what? 1. Okay, after making write enable equal to 1, we need to provide the address. So that means so where we are writing the where you are writing the data, so that we need some address. No, suppose postman, we are sending one letter to that. Okay, so we need a address of the house. No, so that means where we are sending. Okay, we need to address. Without that address and pin code, that letter will not go. Okay, so same like that, you have a like microprocessor or microcontroller or DSP processor. Okay, or this is a FPGA. Like this, you have, this is nothing but master. This is nothing but master, and my RAM is nothing but slave. Okay, so this is RAM is nothing but we call as one IP. Okay, intellectual property. So what you are doing after making write enable equal to 0? Okay, after making write enable, okay, write underscore enable is high, we need to provide the, that means processor is need to provide the address. Okay, the address of the data where processor want to write the address, write the data into that address location. Okay, by using decoder circuit, so by internally processor consists of some decoder circuit. The decoder will generate the address. Okay, which one will generate means internally microprocessor consists of decoder circuit. The decoder will generate the address. Okay, so here write enable. So first you need to make write enable equal to 1. Okay, so this is the write enable equal to 1. We need to make it passage of clock. Okay, and write address is how many bit? So this also we need to provide write address. We need to provide, this is how many bits? 3 bits. Okay, so 3 bits. Okay, so next, suppose for read operation, what you need to do? So that means here address will be like this. So the range is 0 to 7. Okay, so 0 to 7 means address, how it is providing? 0 0 0. So this is 0 address. 0 0 1. Okay, this is 1 address. 0 1 0. Okay, 0 1 0. This is second. Okay, like this you have 1 1 1. Okay, this is 7. Okay, like this we represent the address. 3 bits, 3 bits. Okay, each and every location have the address. Okay, so here this is 0 0 0 address, 0 0 1, 0 1 0, and 1 1 1. Like this have the address. Okay, so for read operation, what you need to do? First you need to make read enable equal to 1. Read enable equal to 1. Okay, so that means whatever the microprocessor or microcontroller or DSP processor, this is a master, want to read the data from the RAM. Okay, so that means write operation is nothing but what? Write operation is nothing but microprocessor to RAM. Microprocessor should write the data into the RAM. Okay, what is read operation? Read operation is nothing but there is some data in the RAM. The data should be read by the microprocessor. Okay, this is nothing but read operation. Okay, for the read operation, what you need to do? You need to make read enable equal to 1 during the passage of clock. Okay, after that you are making read address. Okay, read address. So where you want to read the address, okay, where you want to read the data, okay, so that address you should have. So this is how many bit? 3 bit. Okay, 3 bit. Okay, so hope you understood how we are doing write operation or read operation. So that means suppose first write operation will be happened, and if any data is there, then only we can read the data from the RAM. Okay, first we need to do, so both we can't do parallelly. So first we should do write operation, and next we need to do read operation. Did you understood this? Shall I move forward?
Yes.
Okay, so I will show you with the timing diagram. Suppose I am drawing the clock. Okay, I am drawing the clock. So let us take this is my clock. So let us take this is passage of clock. I am using passage of clock. Okay, passage of clock. So first what I need to do, so I need to make writing the data into the RAM, I need to make write enable equal to what? 1. Okay, I am making write enable equal to 1 during this passage of clock. Okay, so during this passage of clock I am making write enable equal to 1. Okay, so here I am making write enable equal to 1. Okay, so here this is I am making write enable equal to 1. Okay, so during this clock pulse I am making write enable equal to 1. After write enable equal to 1, next what I need to do, that means processor means it should generate the address where it should write the data. Okay, so let us take write address. Okay, so write address is during this write enable only. So you have the address. Suppose in the in the 00 location. Okay, in the 00 location, 00, so 3 zeros location, processor want to write the data into that RAM. Okay, write a data into that RAM. Okay, and after that next data in. Okay, so data in is nothing but data underscore in. We need to provide the data, no? So what type of data you need to write into the RAM. Okay, let us take this is 8 bit of data. Let us take my data is 8 tick binary 1111 underscore 1111. For readability I'm representing like this. Okay, 8 bits of data. Okay, so means write operation is completed. Okay, so what is write operation? First you need to make write enable equal to 1, and during this passage of clock, and next you need to decoder will generate the address, write address, that is 3 bit, where processor want to write the data into the RAM, and after that data during that clock pulse, what data I need to write the data into that RAM. Okay, and coming to the read operation, so what happening, so if you see the read operation, so if you see the read operation first, so this is write operation. Next read operation, what happening, you need to make read enable equal to what? 1. Okay, so here when I am making, suppose when I am making read enable equal to 1, can I get any data? Can I read any data?
No.
No. Why? Because data is not available in the RAM. Okay, so data is not available in the RAM, we can't read. That means processor can't read the data. Okay, here we cannot read. Okay, so that means microprocessor can't read. Why? Because no data is available in the RAM. Okay, can't read. Okay, so after write operation only read operation will happen. Okay, so where it will happen, that means during this clock pulse I am making read enable equal to 1. Okay, I am making read enable equal to 1. Okay, here we can read. Here microprocessor can read the data. Why? Because already data, so after write operation only we can do the read operation. Already data is available in the in this. Okay, so that means here I can write after write operation only. Okay, after write operation we can do the read operation. Okay, read operation. Read operation. Okay, so here what happening, that means here after that so you need a address, you need a address, no? So that means I made the write enable equal to 1, but I need to identify the address. Okay, address of that data. Okay, so here within this that means this is provided by read underscore address. Read underscore address. Here what I am getting, so this is my address. This is my address. This is 000. Okay, so from this address whatever the data is there, that I want to so microprocessor want to read the data. Okay, so this is the timing diagram related to what write operation and read operation. Did you understood any doubts or queries in this?
Understood.
Okay, yeah. So I will go with the coding design part. Okay, so design part I will go with the coding. Design. Okay, RTL design, RTL code. So first, so that means here I want to develop the memory, no? So 8x8 memory. 8x8 memory means you have 8 locations. Each location can have, okay, each location can have how many bits of data? Each location can have how many bits of data? That is 8 bits of data. 8 bits of data. So I need to develop the memory. Can anyone say how to develop the memory? We already discussed. Modeling of memory. How to model the memory?
Using a temp variable temp8, then
Here width means total 8 locations are there, and width is 8 locations, and depth is 8 locations, and width is 8 bits.
yeah. So I mean,
Yeah.
so we need to raise. I mean, declare a variable with reg. Then
Yeah, we need to declare a variable reg. Okay, reg. Next.
7 down to 0.
Yes, 7 down to 0. This is vector. Vector 7 down to 0. Mem of
RAM 7 down to 0.
yes, 7 down to 0. It's correct. Yeah. So you need to use a concept called vectors and arrays. Both vectors and arrays. We already seen this concept, no? So that means whatever the width of the location, I need to declare with what? Vector. Okay, vector, and depth of the location, number of locations, we need to declare with array. Okay, you are correct. Okay, yes, good. Okay, so I am writing the code. So so module, okay, RAM underscore 8 underscore 8. Okay, you need to declare the input clock reset. Okay, write enable. Okay, write enable write underscore enable, and read underscore enable. Okay, read underscore enable, and next read underscore enable enable, and next input write address is how many bits? 3 bits. 3 bits means 2 down to 0. Write address comma read underscore address. Okay. input 7 down to 0, data underscore in, this is 8 bits, no, data underscore in, and input 7 down to 0, data underscore out. So I need to declare the inputs and outputs. Okay, and next what I need to do, reg. I am developing the memory 7 down to 0, mem of that is 7 down to 0, mem of 7 down to 0. I am developing the memory. Okay, I am declaring one integer I. First I want to clear the content in the memory location. For that, what I am doing means always at the rate passage of clock, always at the rate passage of clock, begin if reset. Okay, if reset equal to 1, okay, I am using here I am writing if reset. If reset for I equal to 0, okay, here I am writing, okay, for I equal to 0, okay, I is how many locations are there? 8 locations are there. I that is I equal to I plus 1. Okay, so in the Verilog I plus plus will not work. In SystemVerilog it will work, but in Verilog you need to give I equal to what? I plus 1. Okay, I equal to I plus 1, mem of I that is equal to what? 0. Okay, so normally what you are doing, you are clearing the content of all the locations. You are clearing the content of all the locations, all the RAM locations. Okay, all the RAM locations. Okay, and next so content of all the locations. So next I will write the write operation. Here I will write the write operation. Okay, so what is write operation? So rule. So what is the rule? You cannot apply write enable and read enable at a time. Okay, that you need to remember. Okay, what is the rule? So rule you cannot apply write enable and read enable at a time. Okay, either you can read the data or microprocessor can write the data. Okay, so here else if so how you are giving, that means so first I am giving write enable, no, write underscore enable, that is equal to 1 tick binary 1 and logical and read underscore enable, okay, relational operator, that is equal to 1 tick binary logical equality 1 tick binary 0, mem of that means write underscore in that address location. Okay, write underscore address with non-blocking with data underscore in. Within that address location I want to write the data. Okay, end. So this is nothing but write operation. Okay, next read operation. So how to do the read operation? So read operation is always at the rate passage of clock, okay, begin if reset equal to 1, if reset begin if reset, so data out equal to what? Data out equal to data underscore out, that is 8 tick binary 0 0 0 0 or 0 0 0 0. Okay, else if so you need to make, so during the read operation what you need to do, write enable you need to make as 0, 1 tick binary 0, and read enable, so read enable I am making as 1 tick binary 1. multi binary 1 and data underscore out. Okay, data underscore out. Okay, data underscore out, that is mem of whatever the data present in that location. So microprocessor or controller can read the data. Okay, so that is non-blocking with mem of read underscore address. Read underscore address. Okay, so read underscore address end and end module. So this whatever the read address is there, that user going to provide. Okay, sorry, this so whatever the read address is there. Okay, so read address is provided by the user. Okay, so read address also user is going to provide. User is going to provide. So did you understood this code? Any doubts or queries?
No.
Okay, this is RAM code. Suppose like suppose in this RAM code, this is fixed RAM, no? So fixed RAM, suppose we already wrote the RAM code, this is IP and this is already freezed, but client or customer is asking, I don't want 8 cross 8 RAM, I want 128 cross 8 RAM. So what I can do for this? Any idea?
Can you repeat?
Here this is fixed RAM, this is nothing but fixed RAM 8 cross 8. Okay, so this is one IP, this RAM is nothing but one IP. Okay, so this RAM 8 cross 8 already designed and I freezed. Okay, already checked and verified this design and I freezed this design. After sometimes the client or customer want a requirement that I don't want, he will tell that I don't want 8 cross 8 RAM, I want, so he will tell that I want based on my requirement I want 128 cross 8 RAM. So what you can do?
Should modify it with parameterized.
Yes, we need to use the parameter concept. So here you need to modify, you need to write the code with parameter. So ash, so here I will use, that means parameter. So in this I will add parameter width. So parameter width equal to what? So width, depth of the location, width is 8 only. Okay, width is 8 only, and parameter depth. Okay, here itself I can change the width and depth 128. Okay, and parameter address width. So parameter address width. Okay, address underscore width, this is equal to 128 means how much? 128 2 power, tell me.
7.
2 power 5
7.
7, yeah, 7, 2 power 7, like this you need to initialize. Is it fine? So by using the parameters concept, we are going to this parameters concept, we are going to change the width and depth. So that means dynamically, we are changing the width of dynamically, we can change width or depth. Did you understood? Any doubts or queries? We'll go with the coding part.
Understood.
Okay, yeah. So here, so I'm opening the Vivado tool. So just go to project, open the project. So what is my project means RAM design. Okay, open this project. Okay. Yeah, RAM design. This is 8 cross 8 RAM. Okay, this 8 cross 8 RAM I wrote. Same thing, whatever the code I explained, same thing I wrote. Okay, so that is same thing. So you need to declare the clock and write enable. Okay, write enable I am using, write enable, and this is write address okay, 7 down to 0, 8 bit and 8 bit. I am creating the RAM, and after that I am clearing the RAM location, and after that this is write operation. So always at the rate passage of clock begin, if write enable equal to enable, then begin mem of address equal to dn, end, and d out equal to mem of address. Okay, mem of address, that is read operation. Okay, here itself I am doing the write and read operation. And coming to the test bench, 8x8 RAM. So this is the test bench. Clock write enable, and address d in we need to declare with the rich data type, and d out you need to declare with data type, white data type, and integer I, and you need to instantiate the design connection by name. So my design name and instance name is unit under test. Okay, and after that generate the clock equal to 0 forever. You can use forever or while also, nothing will happen. Hash 5 clock equal to not of clock. So I'm generating the clock with 10 nanoseconds period. Initial begin. Reg variables you need to clear. Hash 10. I'm giving write values. See here. So write equal to 1. For I equal to 0, I is less than 8, I equal to I plus 1, begin, address equal to I, and d in equal to every time 8 tick h AA plus I. So that means initially this is AA. Next time it becomes AB, AC, AD, AB, AC, AD, AE, up total 8 things. This for loop will be executed. After that I am doing the read operation by using for loop only. I am writing, that means reading the data, address equal to I. Okay, reading the data, and also I am displaying also end and dollar finish or dollar stop you can give. Okay, so you can see the simulation, set a stop module, run simulation, run behavioral simulation. Yeah, run simulation, run. We'll see the elaborated design, just how the design is converted, tool is converted your design. So open elaborated design. So this is my RAM, and in terms of RTL RAM, this is converting into the netlist. Like this it is converting, and run simulation, run behavioral simulation. So just see here, fit to page. Okay, so you can see the during write enable equal to 0, so nothing will be happens, and this is write enable equal to 1 means what, write operation is happening. Okay, so that is write operation, that is it is coming in the d in. Okay, so d in, that is AA, AB, AC, AD, AE, AF and B0. Okay, so that is write operation is happening when write enable equal to 0. Okay, and when write enable equal to 1, write operation is happening. Okay, that is coming at the DN. That means this is nothing but write address. Okay, address 0, 1, 2, 3, 4, 5, 6, 7, like this you are getting the data. Okay, and when write enable equal to 0, so here what happening, you are getting the data in the data out. Okay, so AB, so AA, AB, so means microprocessor can read the data available in the data out. Okay, so AA, AB, AC, AD, AE, AF, B0 and B1. Okay, like depending on this address location, in this address location the data is there, so microprocessor or controller can read the data from this this location. This is read operation. Okay, is it fine, the simulation? Any doubts or queries? During this passage of clock only it is happening.
Understood.
Okay, yeah. Next, coming to the parameter, so just I am closing this. So coming to the parameter, as I created the parameter, that is width equal to 8 and address equal to 3, and here I need to create the input address width 1. So here if you see, so parameter, so I need to declare the parameter data width equal to 8 and address width equal to 3. So address width minus 1 is to 0 address width minus 1 is to 0 data in. Okay, so whatever address is 3 means 3 minus 1, 2 down to 0. Address width is 8 means 7 down to 0. Suppose if it is 16 means 15 down to 0, like that. Okay, so you need to create the memory like this. Reg address width minus 1 is to 0, mem of 0 is to 1 left shift address width minus 1, and so I'm checking for read operation, write operation, and read operation. Okay, so this is initializing the RAM to 0, and during the passage of clock, when write enable equal to 1, I'm doing write operation, and otherwise I'm doing read operation. Okay, test bench also same. So here this is RAM parameter test bench, yeah, parameter. So test bench, you can write this same like that, you can write the test bench. Okay, so you need to set a stop module, RAM parameter, right click, set a stop, and again RAM parameter, set a stop, and run the simulation, run simulation, run behavioral simulation. So you can see the output by using parameter, you will get the like so in the test bench what I wrote, so test bench, I gave the values like this: address equal to I, and in equal to 80 h 55 plus I. Okay, 80 h 55 plus I. So that means like this it will take 55, 56, 57 up to 5b and 5c. It is coming in the DIN during write operation. During read operation, we microprocessor can read the data in the D out 55, 56, 57 up to 5c. Like this it can read the data. Is it fine? Any doubts or queries?
Yeah, fine.